So before we get into today's lecture, let's just quickly look at what we did in the last lecture, number 21, which was essentially to review this paper, and this was in 1935, in which basically Einstein, Podolsky and Rosen, they pointed out as to what they thought was the inconsistencies within quantum mechanics at that time. So the way this paper goes is that first they were talking about the Heisenberg uncertainty relation, which is one of the very basic principles of quantum mechanics, at least in the context of one particle systems. And Heisenberg uncertainty relation basically says that a system cannot simultaneously be in the eigenstates of two non-commuting operators. So for example, if position and momentum, these are two non-commuting operators. So a given system cannot simultaneously be in the eigenstates of both these operators. It can be in the eigenstate of either position or momentum, but it cannot be an eigenstate of both these operators at the same time. Another way of saying this is in putting in this form, which is in the form of an inequality, that the uncertainty in x times the uncertainty in p, the uncertainty in position and the uncertainty in momentum, that product has to be greater than h bar by 2. So this is a fundamental constraint that what quantum theory puts on a system. And then this basically says that if we know the position of a system or a particle very accurately, then we cannot have the knowledge of the momentum of the particle with arbitrary accuracy. The accuracy will then be decided by or dictated by this limit, which is h bar by 2. So these two are the statements, that is uncertainty and saying that the system cannot simultaneously be in the eigenstates of two non-commuting operators. They are pointing out the same thing. So this is the first principle of quantum mechanics. Now they use this fact and then they consider a system of two entangled particles, and in the context of two entangled particles, they show that this relation, the Heisenberg uncertainty relation, this relation is apparently violated, and so they point out that this is inconsistent and a theory should not have such inconsistency. Hence quantum mechanics is probably an incomplete theory. Okay, so let's look at their arguments for two entangled particles. So here we have a system where we had two particles that had a common past. That means these two particles interacted in the past, and after that they got separated. And once they got separated, there is no interaction between them. There is no, they are not interacting with each other. And in fact, they could even be space-like separated in the present. So for such a system, then they construct a wave function corresponding to this system, and they choose a very simple function, wave function. This wave function could be anything, but this is the wave function that was chosen by Einstein, Podolsky and Rosen. This wave function is definitely allowed within quantum mechanics for a two-particle system to have. Now this wave function is basically a superposition of, this is a two-particle state, that this is the state corresponding to the first particle, second particle, and that's the state corresponding to the first particle, and there is an integral over p. So this is a superposition of such two particle states over this p. So for such a state, if we make a measurement, we find that the system will then collapse into one of this two photon state. And we see that this one is an eigenstate of the momentum operator of the second particle with momentum minus p, and that one is an eigenstate of the momentum operator of the first particle with eigenvalue p. So if we make a measurement on this two particle system, then we will end up getting one of these. And so the outcome would be that if the first particle is found to be in the momentum eigenstate with momentum p, that means if this is detected, then the second particle is guaranteed to be in the momentum eigenstate with momentum p. Okay. Now then we also saw that this state can be written, this was in the momentum basis, the same state can be written in the position basis. And in the position basis, we see that then this is an eigenstate of the position operator of the second particle, and this is then eigenstate of the position operator of the first particle. So for this state, again, which is a superposition of two particle states over this x, if we make a measurement, we will end up getting one of this term in the superposition. And so we find then that if the first particle is in the position eigenstate with position x, then the second particle is guaranteed to be in the position eigenstate with position x plus x naught. And so what we see is that we see a simultaneous correlation in two conjugate bases, the x and p, and we are seeing perfect simultaneous correlation in these two conjugate bases. But this simultaneous correlation, what it points out that if we make a position measurement here, then that collapses this particle to be in its position eigengate. If you make a momentum measurement here, then that collapses the state of second particle to be in its momentum eigengate. But the first principle says that a system cannot simultaneously be in the eigenstates of two non-commuting operators. But this is what we apparently find, because there is no disturbance, nothing is being done to this particle. Just by a measurement of this particle is deciding what the eigenstate of this particle would be. So this is an apparent non-locality in quantum mechanics, and this is what was pointed out by Einstein, Podolsky and Rosen. And as a result, then they're asked two questions as to if the quantum mechanics is complete, and does it maybe requires additional hidden variables to explain the measurement result. So this was their suggestions of saying that, yeah, maybe we need an alternative theory that would be able to explain the measurement result, but still will not have these kind of features as non-locality and so on. Okay, so hidden variable theory was basically an alternative approach to find an alternative theory that will be free of all these complications. But before we get into that, let's just see this wave function that is in the momentum basis. We see that this wave function cannot be separated like this, that this wave function cannot be written as a wave function of the first particle times the wave function of the second particle. Similarly, if you look at the wave function in the position basis, this is also inseparable. This is the feature we always find, that the two photon entangled wave functions are inseparable. In fact, this inseparability of the two particle wave function and the apparent violation of this Heisenberg uncertainty or the conditional Heisenberg uncertainty, these were the arguments that Einstein, Podolsky and Rosen put forward for kind of saying that the quantum mechanics is incomplete. And these arguments are now seen as what's called the entanglement within quantum mechanics. And here these arguments were formed for the position momentum basis. So here we call it entanglement in position and momentum. So entanglement, as we understand now, it means simultaneous correlations in two conjugate variables and the inseparability of the two particle state into individual particle state. Okay, so far using Einstein's argument, we have defined entanglement, but this is in position and momentum. But we can have other pair of conjugate variables, for example, time and energy, we can also have it there. And similarly, we can have an uncertainty relation or conditional uncertainty relation for time and energy as well. And in that case, we would refer to it as entanglement in time and energy. So the EPR type argument, which is what the entanglement is. It's not that it just exists in this continuous variable basis such as position, momentum, time, energy. It can also exist in finite dimensional discrete basis such as orbital angular momentum. And so here is just one example. This is a state. This is a state in the orbital angular momentum basis. Again, an infinite summation of this two particle state in which the first particle has orbital angular momentum L h bar, second particle is minus L h bar, but they can take in any index L. But again, if you make a measurement out of this infinite superposition, we'll end up with just one term, and for that one term, we'll see that the orbital angular momentum of the first and second particles are correlated in that if the first one is L, the second one is minus L h bar. So again, this we see that the wave function here cannot be written as this separable one, and there would be a corresponding uncertainty relation where we have uncertainty in orbital angular momentum and the uncertainty in its conjugate variable, which is the angle, and the product of these two uncertainties can be less than h bar by 2, and this is what is referred to as entanglement in angle and orbital angular momentum. So an entanglement need not only be in the infinite dimensional basis, entanglement can also be in the finite dimensional basis, and in fact it can be in a two-dimensional basis as well. So in a two-dimensional basis where two basis vectors are a, b, we can write the entangled state as psi a ua plus psi b ub, where psi is the wave function corresponding to the first particle and u is the wave function corresponding to the second particle. This is entangled because we see that this state wave function cannot be factorized like that or cannot be separated like that. So it's an inseparable state and hence entangled. Of course, we cannot have entanglement in one dimensional space, since in that case it would just be a separable product state. So if it is psi a ua, then this is just a separable product state. So this is not entangled. So now let's have a concrete example of this two-dimensional entangled state. We know that the polarization degree of freedom provides two-dimensional basis, and one example of a two-dimensional basis within polarization degree of freedom is the horizontal vertical polarization basis. So if you use horizontal vertical polarization basis, then let's try to write an entangled state. So let's say that for the first particle, psi A is horizontally polarized light and UA is the vertically polarized. Again, for the second particle, psi is psi B, UA is horizontally polarized and UB is vertically polarized. So with that, we can write this two-dimensional entangled state in the horizontal vertical polarization basis like this, 1 over root 2 HHVV. So this is of course an inseparable state because we can't write it like the wave function of the first times the wave function of the second. And so it's an inseparable state, and we also see that this is a superposition of two particle states. One is HH, the other one is VV. So it's a superposition of these two. But of course, if we make a measurement, we will either find HH or VV. So suppose we find HH, then what we see is that the first particle is H polarized and second particle is also H polarized. But suppose our measurement, when we make a measurement, we end up with this term, and so then what we find is that whenever the first particle is B polarized, the second one is also B polarized. So this is a perfect correlation in the horizontal vertical basis that we find here. So this was same as what we did in the EPR case, where we found the perfect correlation in the momentum basis. Then we ask the question, is there a conjugate basis there? So is there any conjugate basis here? So in order to answer that question, we have to ask what is the conjugate to the horizontal vertical basis. So this is the horizontal vertical basis, and we know that a conjugate to this basis is the 45 minus 45 degree polarization basis. And if we have, so we can write this 45 degree polarized light in terms of horizontal vertically polarized light like this. These are the kets. So minus 45, so 45 is H plus V, minus 45, that's H minus V. Similarly, from this relation, we can find the H, we can write in terms of 45 and minus 45 like that, and V, we can write it like 45 plus minus 45. So then if you substitute these expressions for H and V in this one, then we can write the state, the same state which is written in the HV basis. Now we can write the state in the 45 minus 45 basis. So what we find that this is again a superposition of two photon terms. First term is 45 minus 45, second term is minus 45 minus 45. So if we make a measurement, then let's say we either end up with this term or we end up with that term. If we end up with this term, then we have that the first particle is 45 degree polarized and the second particle is also 45 degree polarized. But if the measurement yields this one, then we have that if the first particle is minus 45 degree polarized, second particle is also minus 45 degree polarized. So this is again a perfect correlation in the minus 45 and plus 45 and minus 45 basis. This is the same system, and we find that it is correlated in the horizontal vertical basis as well as in the 45 minus 45 basis. So that's a simultaneous correlation in two conjugate bases. So we have simultaneous correlation in two conjugate bases, and it is also an inseparable state, and this is what we refer to as polarization entanglement. So again, we have tried giving a very similar interpretation here as the Einstein-Podolsky-Rosen argument for position, momentum operators and variables. And here it is for polarization, but just polarization is two-dimensional and X and P these are infinite dimensional. So what we have seen is how EPR arguments can be formed for infinite dimensional continuous and discrete basis as well as for the two-dimensional basis. So now what about EPR's question, that is quantum mechanics incomplete? Does it require additional hidden variables to explain measurement result? And what about the non-locality in quantum mechanics? So there have been several efforts, and in terms of hidden variable as suggested by EPR, in order to get to the apparent non-locality that we discussed within EPR argument. This hidden variable is just an alternative approach to find a theory that is able to explain all the predictions of quantum mechanics or able to explain all the measurement results that we see, but without having to use the notion of wave function or a state or entanglement or anything. So this was the effort. So we have seen that the science EPR argument can be constructed for infinite dimensional, continuous, discrete as well as two-dimensional basis. So of course a hidden variable theory can be worked out for infinite dimensional basis as well as for two-dimensional basis. So here we will actually just describe the hidden variable approach through a two-dimensional version, through two-dimensional theories only, because that's simpler. And once we show the failure of this theory for a two-dimensional version, then we don't need to do any further, because here we'll have a theory, quantum theory, that is able to explain all the experimental results. But even in two-dimension, we find that there are certain experimental results that the hidden variable approaches were not able to explain. Okay, so with that, let's get into the hidden variable interpretations of quantum mechanics. Here again, I will not get into the details of the theory itself, but I will just point out a few experimental results that this theory is not able to explain, and that would be sufficient to kind of illustrate that such theories cannot replace quantum mechanics. So here is an entanglement quantum mechanical setup that we have a source of entangled photons. So these are the two entangled photons, and they have this correlation which we call entanglement. And then we also have this source, in fact two independent sources. Within the source, within these two sources, we can have several rules as to how these sources operate, but these sources are independent as far as emitting the photons are concerned. So now let's look at one measurement outcome that somebody sees in the lab, and then we'll see if the quantum theory or the hidden variable theory or both are able to explain that or describe this measurement outcome. So the first measurement outcome is that somebody does an experiment and you have these two photons coming. Again, we don't know whether it is a source of entangled photon or we can describe it as a source of two independent sources. That's the theory, but what one sees in the lab, in the experiment, is that we have these two photons coming in, and then an experimenter is doing some measurements over here. Again, in this setup also we have these two photons coming in and we do these measurements here. So one of the measurement outcome is that one finds that if the signal photon, which is this one, let's say, is measured to be horizontally polarized, then the idler photon is also horizontally polarized. And whenever signal photon is found to be vertically polarized, idler photon is also vertically polarized. So that's the measurement outcome somebody has, and now one has to see what kind of theory will be able to explain this measurement outcome. So let's first take quantum mechanics. Can we have a wave function description that can explain this measurement result? Of course we have, and which is this wave function. So if we have a two particle wave function like h and v, then this would be able to explain this kind of measurement result, because this says that of course if you make a measurement, the system will collapse either into this one or into that one. If it collapses here, we find that whenever it collapses here, we find that both signal idler are horizontal. Whenever it collapses here, we find that both signal idler are vertical. Now, can the hidden variable model, which is having two independent sources, can it also explain the result? So yes, it can also explain the result. And in what way? So let's say if you have two independent sources, and let's make a few rules as far as how these sources can emit photon. So the first rule is both sources emit simultaneously and emit the same polarization. So both the sources are emitting at the same time and the same polarization. And then we have the 50% of the time both sources emit horizontal polarization, and 50% of the time both sources emit vertical polarization. So with these three rules, we can see that we are able to describe or explain this measurement outcome. We do not need the wave function description to explain this measurement outcome. So is this entanglement? This measurement outcome that we see, is this entanglement? Answer is no. Let's look at another measurement outcome. Here in this case, an experimentalist sees that whenever a signal photon is measured to be 45-degree polarized, the idler photon is also 45-degree polarized. And whenever signal is minus 45-degree polarized, idler is also minus 45-degree polarized. So if this is these are the measurement results reported by an experimentalist, then the question is if quantum mechanics can explain this result. So of course a wave function which is of this form, 45 minus 45 minus 45 would be easily able to explain this measurement outcome, because this is a superposition of these two photon terms. If you make a measurement, the system either collapses into this term or into that term, and so if it collapses into the first term, we have that the first particle, both the particles have a 45-degree polarization. If it collapses into the second term, then both the particles are minus 45-degree polarized. So now the question is, can hidden variable model also explain these measurement results? So here, what are the rules? So again, we can have these set of rules that both the sources emit simultaneously and emit the same polarization. 50% of the time, both sources emit 45-degree polarization, and 50% of the time, both sources emit minus 45-degree polarization. And with these three rules and with these two independent sources, we would be able to explain these measurement outcomes. So is this entanglement? No. And we have seen that this result, this measurement outcome, this just represents a correlation in one basis. Similarly, the first measurement outcome that was in the horizontal vertical basis, that also represents correlation in only one basis. So, and we know from EPR arguments that now that if the correlations are in both the bases, then only we call it entanglement. Okay, so now let's look at the third measurement outcome. Here an experimentalist report that whenever signal photon is measured is found to be horizontally polarized, idler is horizontally polarized. Whenever signal is vertical, idler is vertical. At the same time, whenever signal is measured 45 degree, idler is also measured found to be 45 degree, and whenever signal is measured to be minus 45 degree, idler is also found to be minus 45 degree. So these are the set of correlated measurement results that the experimentalist is reporting. Now the question is, can quantum mechanics explain this measurement outcome? And the answer is yes. We have this wave function. This wave function will explain this results, these measurement outcomes. And of course, this wave function, the same wave function, can be written in the 45 minus 45 degree 45 basis like this, and this would be able to explain these measurement outcome. Now the question is, can the hidden variable theories, hidden variable model using two independent sources, can they also explain these measurement outcomes? And the answer is no. In fact, the challenge is, no matter which and how many set of rules we make here on these two sources, we would never be able to explain these measurement outcomes. But the quantum mechanics of course can do, but hidden variable theories will never ever be able to do. Of course, we can do that both sources emit simultaneously in the same polarization, and then one very plausible theory seems that maybe they can emit 25% of the time they emit horizontal, 25% of the time they emit vertical, and so on for 45 minus 45. But we will quickly see that if this one emits two horizontal, but experimenter has no idea, and experimenter this time is measuring both vertical, horizontal and 45 minus 45 degree basis. So suppose there is a horizontal photon coming in, but the experimentalist is measuring in the 45 minus 45 degree basis, and since a horizontally polarized photon has 50% chance of being found 45 and 50% of chance of being found as minus 45 degree polarized photon. Then when you have H and H here, and but if the experimenter is measuring with a 45 minus 45 polarizer, then there is a chance that we can get uncorrelated result, that one detects a 45 and minus 45 here and vice versa. So this 25% for all the four polarizations, that model will not work. And the challenge here is that no set of rules will be able to explain this measurement outcomes, which are basically simultaneous correlation in two conjugate bases. So is this entanglement? Yes, this is entanglement. And through this one example, what we have shown here is that the hidden variable theories are not able to explain this specific result, that is the simultaneous correlation in two conjugate bases that we see here. But quantum mechanics is definitely able to explain, and these things have been now seen experimentally and kind of proved beyond doubt that yes, hidden variable theories do not work. So this is, here we have just given an introduction to the hidden variable theory and kind of shown that with this particular example that and for the two-dimensional case that it actually doesn't work, and hence it cannot replace quantum mechanics. So we will not be doing the hidden variable for the continuous variable and so on. This is just sufficient to kind of show that it cannot replace quantum mechanics. So here is a kind of chronology of how these foundational debate about quantum mechanics can proceeded. So 1935 we had EPR paper, and then about after 15 years there was hidden variable theories that were suggested and worked out by David Bohm, and there's several other work. I'm just pointing out two here. And then until 1964 there was no way of finding out whether we can actually experiment. There was no way of finding out whether one can have hidden variable theories or not. So in 1964 John Bell he proposed an inequality, and he then showed through rigorous math that if that quantum mechanical results can actually violate this inequality, but the hidden variable theories won't be able to violate. And then in 1980s, 90s, there were several experiments showing the violations of Bell inequality, basically showing that hidden variable theories basically cannot replace quantum mechanics. So there's several experiments that have actually been done. In fact, people are still making more and more complicated hidden variable theories, and then again then people are following that up with more and more updated version of Bell inequality violation. So in the next lecture, we will look at this Bell inequality in its original form that was given by Bell. This was given again for two-dimensional systems. So we will look at the Bell inequality. So for today's lecture, we will stop here. Thank you.